Good morning, good afternoon, everyone, and welcome to the October 5th edition of Canvas. Hope everyone had a good weekend. Today's speaker is Wes Fraser, who currently works as a postdoc research associate at NRC Hertzberg. Wes got his PhD in 2004 from UVic and has been heavily involved in a lot of cool research on the outer solar system. So today we're going to have a bit of a unique talk where the audience will get to choose which rabbit hole Wes takes us down at various points during the talk. And so I'll be initiating polls and you will be able to select where you wish Wes to lead us. And so with that, I'll hand it over to Wes. Take it away.
Thanks, Dennis. Yeah, I've adopted similar sort of choose your own adventure styles before to generally good reception, though there has been a couple negative points in the past. So if you don't like what I've done here today, or you do like what I've done here today, please let me know either way. That email address, I'll be happy to see any feedback you've got. On to the science, though. I've titled this one After the Dust Settles because I think that is a good piece of sort of context that I like to keep in mind about what it is I'm actually studying when I look at icy bodies in the solar system. I say dust, even if these things are hundreds of kilometers across, because in the context of looking outwards, the dust is the only thing we can see that is analogous to these objects in sort of exostellar systems. So that's what I call it here. What I've tried to do today is to give some idea of context for the buildup of planets from systems like this. And so this is really what a lot of astronomers are trying to work on right now, is how do we go from clouds of dust and gas to stars, planetary systems, and all of the stuff that we're currently seeing in our own solar system. I've decided to give a little bit of a walkthrough that you would see from sort of a debris disks or star and star formation type talk. So that's what we're seeing here. On the left is just a fantastic picture, I think, from JCMT and Herschel of well, I guess you would call this a star formation region. I'm sure I'm going to use some jargon incorrectly from the star formation side, and Doug might be rolling around in his chair right now. But the idea is I'm working on the details of some of the steps that are in between the one on the left there, the forming stars. I guess you can't see my mouse, sorry about that. And uh, this is, of course, a picture from Juno of Jupiter right from the south, which I think is absolutely fantastic. Um, so generally the picture that people try to keep in mind when thinking about star formation is this graphic or sort of cartoon diagram that Nyenka provided to me. A lot of these graphics Nyenka has helped me out in getting a hold of, and thank you very much for that. The idea is you would start from gas, gas and dust. Of course, we now have just learned that there is in fact water tied to the dust, which I think is pretty awesome. So it's gas, dust, and water. I'm happy to state that. And as things collapse, you can enter these sort of class 0 through class 2 protostars, if you want to call them that, and eventually planets collapse out of that, and you get these planetary systems. And we've got some great examples over the years of various stages of that. So here's one of my favorite pictures of all time, the Pillars of Creation from NASA, taken back, believe it or not, 1995 with the HST. This is in the Eagle Nebula, and the idea is this is a sort of moderate stage of the collapsing of a cloud into clusters of stars. At the heads of, or at the tops of each one of these pillars are groups of stars that are in the process of actually forming star systems now. If you look a little bit closer to home in the Orion Nebula, you can see a little bit later of a stage. These are the famous proplyds of Orion. I think there's something like 100 of these now known, which is really amazing to me. The idea here is that these are later stage, and so each one of these is an individual stellar system that is at some level of hidden by the dust that is forming the planetary systems in each one of these proplyds. And so you can see, like down to the second one from the bottom left, there is a beautiful example of a disk with a star that isn't too well hidden, or a lot of the ones up at the top are stars that are completely masked out by the dust. And so the idea is there are planets forming in the disks of these systems. Even later still, so this is some work by Nyenka, and is again one of my favorite uh, compilations of picture. This, I was totally blown away by the first time Nyenka showed this in a talk at HAA. Here are various what I would call protoplanetary disks, though it might not be so proto, because a number of the ring structures that you see in these disks are presumably caused by planets. I think that's a pretty safe bet at this point. And there's various sort of stages of evolution that you see in here, but this is fantastic, right? This is sort of the dust that you see and the sculpting of that dust by those planets. Eventually, once the dust has cleared and settled down, you end up with discovery, or you end up with protoplanetary or planetary systems, excuse me, like what we now have seen with Kepler. I think C might not be fair. Of course, we only see the transits of the planets themselves in front of their stars, and from that get to build up what the planetary systems look like. And so this is a Kepler orrery, is what they like to show these as the massive variety of planetary systems that we get. I've done two things here which are unfair to Kepler. One, I've chosen one from 2013 because there are so many planetary systems now that Kepler's found. You basically can't make an intelligible plot on a screen and show them all at the same time. So I choose one from a number of years ago just to sort of keep it visible. The other thing I've done is to take a screen cap, just a single frame of the orrery. Most of the orreries that you see are animated. So each one of these will have their planets orbiting around their star, and you can see the eccentricities and resonances and stuff. It's really beautiful, but it's also motion sickness inducing if you stare at it for a bit too long. So I like the screen cap version better. So that's 5 minutes on how you go from dust and gas to planets. And obviously there's a lot of detail in those stages that a whole bunch of people are working on. So of course, Nyenka working on the clearing of the dust. I personally am working on how you form planetesimals once you actually have a disk. And the leading theory, or the leading idea for that, stems around the streaming instability. And so imagine this is a simulation I'm about to show of the streaming instability itself. And so this box is actually a cutout of a disk. So instead of looking at an entire system, a ring, what we've done is made the simulations a heck of a lot more tractable by looking at a disk, or a section of a disk, and imagine that box is rotating around a star. And so this is a gas and dust together. And if you just let it go, I promise this isn't galaxy simulations, even though this looks a lot like the formation of galaxies. As you let this gas orbit around the sun, the interaction between the gas and the dust will cause dust to be squeezed together into streams. That's what you were seeing right at the beginning here of this, and it kind of condenses. But then the back reaction allows those streams to sort of catch up on each other. That's the so-called streaming instability, where if the back reaction from the dust onto the gas is strong enough, you can actually allow the clumps to, or you actually allow clumps of dust to form. And when they get big enough, they basically become detached from the gas itself. And you're left with things that in this simulation look an awful lot like galaxies, which I think is kind of humorous. And so this is the current favored idea of how you go from dust to gas, or dust in a gas to planetesimals outside of the gas itself. And there's a lot of reasons for it, which we might talk about in some detail, depending on which path you choose later. The other part of this streaming instability is the actual formation of the planetesimals, and then again the planets themselves. What I've shown you here is how you can clump a bunch of dust together, but these are just clumps. There's not enough resolution in these hydrodynamic simulations to actually form the planetesimals themselves. And so a few years back, one of my students, Jamie Robinson, and I embarked on a project to try and understand the actual formation of planetesimals. And so what I'm showing you here, again, imagine a cutout of a disk, but now this is centered on one of those clumps from the previous simulations. And each one of these particles represents dust. That's a bit unfair because these particles are still, a couple kilometers across. But that is actually about the scale of what kind of dust would be entrained in a clump by the gas in the outer solar system. So, one might call these pebbles in a simulation. Pebble can mean a very different thing if you're way out in the way out in the solar system, and the gas is tenuous. But the idea is, oh, whoops, sorry, go back to this. On the left here is the full cloud and the full simulation box that we're talking about. The twisting of that cloud you see is both a combination of the gravitational collapse of the cloud itself, as well as the Kepler shear as this box rotates around, in the sense that the sun is on the left. The stuff that's closer to the sun rotates a little faster, and the stuff that's away from the sun rotates a little slower, and you get this twisting effect that occurs. On the right is a zoom in of the most massive particle that shows up, and that's actually shown by the red cross on the left. And you can see here, not only has a planetesimal quickly formed out of the cloud, you actually have a binary system that's formed here. And the really neat thing about the streaming instability followed up by a collapse of a pebble cloud, like what you see here, is that you do form a huge number of binaries. And it's the presence of binaries in the outer solar systems in the Kuiper Belt that is basically the reason why we think there is some veracity to this idea. And of course, the most startling example of all was the new results of the New Horizons flyby of Arakoth, which you can see in the bottom left there. That is a small system, but presumably formed in a very similar way. And then through tides and interactions with the small amount of gas that'd be left over in this process, you can bring those two binary components together and have them stick to form the nice red snowman that we actually see there. So Arakoth is the most startling example of one of the detailed processes that we think has occurred, at least in our solar system, and very likely in formation of planetary systems in general. I haven't talked about the formation of planets, like how you get something like Jupiter from this. It's actually a very similar process in the sense that we think the majority of accretion onto planets and planetesimals themselves is from the pebbles and not from macroscopic bodies hitting each other, in the sense that you don't form Earths and then have the Earth smash together and form Neptunes and then have the Neptunes smash together and form Jupiters. Rather, you form an Earth, and then through gas physics, a bunch of pebbles and such are focused onto the Earth, and very quickly you grow up into bigger bodies. And when I say quickly, I mean really quickly. This binary formed in about 1/3 of the time it takes for an object to go around the sun at the distances we're talking about here. So about 100 years to go from dust and pebbles to macroscopic bodies like what we see in the Kuiper Belt. So that's a pretty crazy idea. I personally was quite uncomfortable with the whole thing at the beginning of when this idea was being talked about a decade ago, but there actually seems to be a lot of evidence for it nowadays. Okay, great. So this is how we can, one idea about how we can form planetesimals and then eventually build up into planets. The final stages of dust settling involves a migration. And so there is good evidence, which we might talk about depending on the path you choose, that the solar system was originally a lot more compact than we see it now. And so instead of Neptune being at 30 AU, we think Neptune probably formed closer to 22, 24 AU or something like that, like in this animation that I've drawn here. This is a rendering of a migration simulation I did. The rings here are the orbits of the gas giant planets at any given time, and each one of those particles that you see there is essentially a Pluto mass-sized body. And so there's only about 1,000 in this, but it's enough to get the point across. Down at the bottom there, you can see the semi-major axes of the 4 planets, and you can actually see for yourself that they are starting to migrate out. And the idea is there's interactions between the disk of Plutos and Neptune that causes Neptune to gain angular momentum and move outwards, and a bunch of these objects to fall in and then get punted out of the solar system. And so they clear out. And once Neptune penetrates the disk, as you can see it's done here, it migrates out very quickly. And voila, you can actually put Neptune into its place. And so we have some pretty solid evidence that this process has occurred, which is very interesting because it suggests that the pictures that we're seeing from ALMA have a long ways to go before they're finished forming, right? I would call this a formative process, even though the planets themselves aren't really growing in this. Our solar system certainly was evolving or growing up. Maybe it's like the puberty part of of planet formation. One thing I'd like to point out here, I'm just going to run this animation again. Uranus, in this case, the red one, the third planet out, it's jiggling around a lot. And this is actually the reason for this jiggling is it's actually a very unstable process. This is one particular rendering or a simulation that results in a smooth outward migration. But if you were to run this again with a slightly different configuration of planets or a different amount of mass in the proto-Kuiper belt, you can actually get this whole thing to catastrophically self-destruct, and planets will interact with planets, things will get floating around all over the place. Sometimes you actually get planets being ejected from the stellar systems completely, and this is part of the source of the variety of planetary systems that we see with Kepler. And it just so happens that we got really lucky because in the process of the gas giants bashing themselves around, oh, sorry about that. Sorry about that. I hope you can still hear me. Yeah, usually what happens in these,
Wes, we have a
yeah,
question raised in the chat window. Do you want to take that now?
I can't see it.
I'll read it out to you. I'll read it out to you.
Please do. Yeah. Sorry. Thanks.
Okay, how do you model collisions? Some collisions would result in fragmentation and others in merging of the colliding bodies. How do you
That's right.
distinguish between these cases?
So the absolutely great question. I'll go back to the previous. I'll go back to this one here. The collisions between the Plutos don't matter too much. They produce a lot of dust, but there's not enough mass in that material to dominate the evolution of the system. It's still the macroscopic interactions between those Plutos and Neptune that ultimately drive the migration. The collisions between the gas giants themselves are very important because you can produce quite exciting systems from it. For our case, we don't have to worry about it all that much because, of course, we didn't have those collisions, because if we did, those collisions would not only destroy the gas giants themselves, but also the terrestrial systems, like the Earth, for instance, probably wouldn't exist. But for simulations where you're wanting to consider systems like what we see with Kepler, where you have a lot of hot Jupiters, for instance, collisions are an important detail there. And you can't just consider things elastic and merging. There's a lot of gas physics involved, and it's a whole field of consideration on its own. I hope I kind of gave a hint as to what people do there, but it unfortunately is a lot outside of my particular wheelhouse. I pay attention to it, but I don't do it myself. Is that all right? I'm going to carry on. So, anyways, after a migration like what we see there, we're left with this stuff behind. And this is ultimately what I'm interested in. So here is a rendering from the Minor Planet Center, generated a few days ago, of all the known asteroids. So the main belt is in green, the near-Earth asteroids are the red things, and the Jupiter-Trojan asteroids are the blue ones. These are, of course, the ones in the leading and trailing Lagrangian resonances, or Lagrange points. And there's gajillions of them, right? There's more than you ever would want to count, which is pretty awesome, because these things can be used as a historical record of the planet formation process, basically with what is left behind, what didn't eventually catch the bus to school, is informative about what the bus was actually doing. And so that's the perspective that I take in trying to understand the planet formation process. When we move to the outer solar system, we can make graphics look a little bit better because there aren't gajillions anymore. There's only thousands. And so this is a rendering I finished over the weekend of the current known Kuiper belt. I'll run this here. That solid line, by the way, is the trajectory of New Horizons, which is represented by that triangle there. Gas giant planets, of course, are the blue or the colored circles. And each one of these individual points is a real known object. The trajectories themselves are, in fact, real because it's an n-body simulation, not just taking the current orbits and projecting them forward. And to give an idea of scale, the blue, what we call scatter disk objects, these are objects that are interacting with Neptune on million-year timescales, are shown by about one quarter of them are shown by those blue orbits there, to give you an idea of how big the Kuiper belt actually is. Of course, we can only see the objects that come close to the sun, and so that's why you see a clustering of the blue things here. If you run this long enough, you can actually see a lot of these objects moving away from where we can see them to becoming much too faint. The colors here represent different orbital classes, which may become important later. Some are in mean motion resonances with Neptune, say like Pluto. So there's a whole class of what we call the Plutinos. These are in the 3-to-2 mean motion resonance. The yellow ones are in the 2-to-1. Sorry, I should mention that the 10 circles that you see, these are the dwarf planet candidates. We always have to put candidate on the end of dwarf planet because that term itself is relatively poorly defined in the sense that we don't actually understand the rheologies of these systems. So we can't, or each one of these planetesimals, and so we can't tell you if they're gravitationally relaxed or not. So they're big enough that we think they're probably gravitationally relaxed, but we can't actually say for certain if they're relaxed or not. Anyway, I love this animation for perspective because, of course, Pluto is just on the inside of that, or just on the outside of that second dashed ring there, and so the solar system itself really is quite huge. And that animation also shows some of the dynamical structure, which has been what I call the dynamical lever arm, the main source of evidence for planetesimal formation and planet migration. And so the buildup of objects in the purple pillar here on the left in this eccentricity inclination semi-major axis plot, these are the Plutinos. And we think that Plutinos were captured into that resonance by an outward migrating Neptune, basically acting as a snowplow to pick up objects into that resonance. And of course, you can see other resonances in here, like the two Tinos, the poorly named ones, which are in the 2-to-1 resonance at 48 AU. And so I should be using my mouse here, which you can't even see. Never mind. And of course, then there's a few objects that are Trojans of Neptune, which you can see at 30 AU as well. There's a lot of dynamical structure here. I won't get into it in too much detail, but it is this dynamical structure that tells us Neptune and by extension, the other gas giants have moved. And then the pictures like this frame of 4 Kuiper belt binaries on the right, they're the evidence of basically of the streaming instability followed by pebble cloud collapse, because about 30% of at least the clump of red objects that you see on the left inclination plot, the so-called cold classicals that are dynamically cold and in a very small region of the Kuiper belt, 30% of those are actually known resolved binary objects, which is pretty crazy if you ask me. It argues that a large fraction, maybe 100% even, underwent a formation through pebble cloud collapse. We might talk about that depending on your choices today. Finally, on to my direct research. So apologies to those who have heard about Col-OSSOS before, but you're going to hear about it again. Colors of the Outer Solar System Origins Survey is a large, long Gemini program that I've been running with the help of a number of people, some of which are attending this talk right now. We've been running since 2014 on Gemini and then CFHT behind it to gather basically colors, multi-band UV, optical, and near-IR colors of a bunch of Kuiper belt objects with a lot of the properties of a survey that astronomers like, including brightness completeness and understood biases and so on and so forth. The idea is to start to use the apparent compositions of Kuiper belt objects as an additional lever arm on formation. Because if you've noticed so far, I've mentioned very little about the material makeup of anything that I've talked about today. And it's just something that we're starting to understand a little bit now. And so what I've shown you here, what I'm showing you here is the 5-color plot. This is basically the main data product of the Col-OSSOS survey, where we've got G minus R on the bottom, the typical middle optical color, and then U minus G, R minus Z, R minus I, and R minus J for the near infrared. These filters were chosen as useful for understanding Kuiper belt spectra, which we'll probably talk about a little bit later. And also the balance of spending too much telescope time on the ground. So U comes from, U-band comes from the CFHT. When we observe on Gemini, the observers, whether it's our team or the Gemini observers in Q mode, call up CFHT and say, hey, can you join us? And then the 2 telescopes flew to the same spot, and we get simultaneous colors in a lot of these bands, which is really freaking awesome. I've been very blessed to be able to do this. The main data product is, or the main focus is UGRJ, so basically the top panel here. And the reason for this is because we know that these 4 filters are most useful in separating out the known compositional classes of Kuiper belt object. And so if you stare at this figure long enough or keep up with the literature, you would see in G minus R and R minus J space a gap, a diagonal gap of where there are no objects no known Kuiper belt, very few known Kuiper belt objects that occupy that space. And so I've tried to trace that out with this blue dotted line here. And it basically divides out the 2 known compositional classes. The very, very unoriginally named very red and less red. It used to be called red and neutral, but the problem is there's no actual there's no neutral Kuiper belt objects, in the sense that in the optical they're all red. It just depends on if they're somewhat red like our skin, or very red like bitumen. And so that's where the names of those 2 classes come from. You'll see that the Col-classicals have been identified in red points here. These are dynamically interesting, and from Rosemary Pike's work, there is evidence that in fact they occupy a 3rd class, which I'm not going to talk about too much today, but the idea is, from a survey like this, you can go back and work out what the compositional structure of the protoplanetesimal disk looked like. So this is when planetesimals existed in the disk, but hadn't yet been pushed out into the Kuiper belt through planet migration. And so here is the cartoon picture that we like to show when understanding this. There were probably 3 classes of 3 compositional classes in the disk themselves. In the cartoon in the bottom here, the black and blue regions reflect the less red and very red compositional classes. And then the red section out at the end, beyond about 39 AU, those are the Col-classicals, and we think they are unique in their surfaces, and they're also formed in situ. And so this is, you can put all of these pieces together to start to work out what the composition of the actual disk itself looked like. And so that's where, that's the whole idea Col-OSSOS is predicated on, is to try to use what we know about Kuiper belt surfaces to tell us a bit more about the evolution, the late evolution of the solar system. And with that, we're to our first choice in choosing your own adventure. Door number 1 will lead you to a discussion of the basic, what we think we understand about TNO compositions, to trans-Neptunian object compositions. So these are objects that are in and amongst the gas giants or the Kuiper belt, or even further out into the scattered disk. And then door number 2 is a formation model that we think is what gives us the differences in compositions between the different classes that we see. So Dennis, if you could lead a vote on that, that would be great. I'll see if I can't find my mouse. There we are.
Mute myself. I'm going to launch the poll. Please respond.
Give it a few seconds here, of course.
Yeah, I can see the numbers coming in.
Great. I'm not going to vote.
Okay. Okay, a few more seconds. We're up to 21 out of 26.
Awesome.
Okay.
That's great. Thank you, everyone. This is fun.
Yes.
I couldn't decide what I wanted to talk about, so
I think
really
it's
glad
pretty
you're doing it for
clear. So we're going to go with the computational class formation model.
me. Door number 2. All right. Unfortunately, you've chosen the only slide with an equation. I like to stick to nice looking pictures and such, but if we go back to our probably second year undergrad talking about astronomy, there is this thing called Jeans escape. Jeans, obviously being a very smart individual, realized that if you have a thermal, a cloud of gas in thermal equilibrium, the hot end, or the high velocity tail of that cloud, can reach velocities that, if that cloud were in fact an atmosphere, those velocities are higher than the escape speed of the planet or whatever body you're around, and you bleed off gas. So this is the reason why we lose hydrogen and helium to space around the Earth, is through the process of Jeans escape. Um, for nearly atmosphereless bodies, like what we see in the Kuiper Belt, we think this is the dominant process for the loss of sublimatable material. And so planetary astronomers like to use terms like volatile. And so we'll talk about volatile ices. These are ices like, say, methane or nitrogen that are frozen, but just barely so, because there is in fact a sublimation pressure above the icy surface, and that pressure will bleed into the atmosphere and then very quickly leave through Jeans escape. And so it just happens to be that Pluto is able to keep its nitrogen ice in an atmosphere because it's massive enough. And so there's two terms that are important here for Jeans escape. Oh, where did my mouse go? Oops, let's go back. Oh, where'd it go? Well, okay. No mouse. You can see in the right-hand side of this equation lambda. Lambda is basically the balance between the gravity of the planet, or in this case, the Kuiper Belt object, big M, and the thermal temperature of the ice, or of the atmosphere itself. And then the second term that's important is the vapor pressure of the ice from the solid surface. And so, as it turns out, vapor pressures, sublimation vapor pressures, are exponentials. And they're very, very strong exponentials of temperature. And so when you combine both of these together and understand the vapor loss rates from Kuiper Belt objects, there's basically two parameters that matter the most: the diameter or mass of the body in question, and the temperature of the bodies. As it turns out, Kuiper Belt objects all sit around 35 to 40 Kelvin surface temperatures, and we know of objects that are 100 kilometers in size and larger. The veracity of this idea is given to us by seeing volatile ices on some large bodies, but not on others. So for instance, Pluto is a very good object in the sense that it has nitrogen, CO2, CO, and CH4. These are three materials that are right on the edge of being completely lost to space if Pluto were ever so slightly warmer or ever so slightly more massive. And you can actually draw sort of what I call switch lines, that if you're on the right side or the bottom of the line, you are either massive enough or cold enough to keep the ice, and on the left, you lose everything. And so we can see that Pluto, Triton, Eris, Sedna, those are all volatile rich bodies from their spectra, and they all happen to fall on the right sides of those lines. There are some bodies like Orcus that they're very, very hard spectra to negotiate, but it seems like there might be some volatiles on it, and so these lines might need to move around a little bit when you consider all of the details of the model. But in general, this idea of sublimation followed by Jeans loss can explain the volatile budgets of the large planetesimals over the edge of the solar system. Now, if you take that to its extreme in thought, there are a lot more materials that aren't quite as volatile as, say, methane, but are still volatile on 4 gigayear timescales, or in some cases, tens of thousands of year timescales. And so if you look at a whole bunch of ices that we think that we do see in comets, but we don't see on the surfaces of Kuiper Belt objects, you can draw these lines. So now this has been inverted from temperature to formation distance. And the idea is that at the beginning of planetesimal formation, all planetesimals formed with the same general budgets of stuff, in the sense that they all probably had ammonia, they all probably had methanol, so on and so forth, because formation, as we think, is a very quick process. But through Jeans escape over some relatively quick amount of time, all the small things lost some of those materials if they were too close to the sun, because they were just simply too hot. And so what ends up happening here is that the ones that formed close lose a bunch of organic materials that the ones that formed further away were able to keep. And then over the age of the solar system, through irradiation and whatnot, you actually get two different chemical pathways that lead to different surface types. And so the less red material is probably more organic poor. They have less organic material on their surfaces than the very red stuff, which has more organic. And now what we're currently trying to do is to understand through Col-OSSOS where the dividing line, if there was such a thing, a dividing line between the less red and more red or very red materials was, so that we can try, or where they formed, so that we can then try and work out what materials they might be missing, and then figure out what chemistry differences would occur, and actually go look for those materials with, say, JWST or something like that. And so this is currently the leading model that allows you to go and end up mix objects from 20 to 30 AU and pump them out into the Kuiper belt, but end up with two different kinds of surface that we see. Some people have speculated that H2S is the most likely, even though it has a distance dividing line of about 12 or 13 AU there, as you can see. We'll see. JWST is really going to tell us which of these materials happen to be still left over on the bodies. But anyway, that's the idea about how you can form one class and another class in a disk and then scatter them out into the Kuiper belt. Now, if I can find my mouse again. Off to the next poll. This is, again, very compositional, but I want to talk about some of the oddities, or, again, another model about surface compositions. I haven't told you anything specific about the compositions of Kuiper belt objects, so hopefully you'll get a little bit from either of these doors. So Dennis, if you could run the next poll,
Poll
please.
is launched.
Thanks.
Please vote. Okay, we got 18 of 25, 19, 20. Oh, it's pretty obvious. I'm going to end polling. And the winner is the asteroid in the Kuiper belt.
Yes, this is a fun one.
Sounds like a mystery novel almost.
Okay, so I've talked about compositions a little bit and a compositional model of objects, but what I haven't done is talk about the compositions of Kuiper belt objects themselves. And so here is a very good spectrum of a checklist. A checklist is actually not a Kuiper belt object, it's a Jupiter family comet, but what I haven't told you is that Jupiter family comets are objects that fell in from the Kuiper belt. And we know from watching their evolution that the surfaces don't change all that much on the time scale it takes to fall from 30 AU to 5 AU. And so the best spectra we get of Kuiper belt objects are actually from JFCs themselves. And what ignore the title, the atypical one is coming in a second. This is actually very normal for what you see for a Kuiper belt object, in the sense that you have a red optical region, a less red near infrared region, a few telluric lines contaminating your spectrum, which are those dotted regions there, and a whole lot of nothing going on. There is almost no compositional information in this whatsoever. There's no hint of water ice at 1.6 microns. All you got is this red slope, and it's damn annoying because we don't know a whole lot about TNOs. What we know is that that red slope is caused by the so-called optical gap, which is basically when you have a carbon and hydrogen-rich organic material, like, say, bitumen or the human skin or whatever, there are valence bands of basically conduction bands of the electrons that are on the outer bounds of the CH bonds, that when they get impinged on by a high energy photon, they become conducting across the material and you absorb. So this red slope is caused by an overlap of a whole bunch of different valence bonds in disordered materials. And that's about all we know. We presume that there is silicate in here based on density measurements of the binaries. We presume there's water ice in here because we do see water ice absorption on some KBOs, but not all. But in general, this red slope is all we really get. And so this is why Col-OSSOS is actually kind of useful, is because we don't need spectra, you just need broadband colors to characterize something like that. Anyway, EW95 doesn't look like that. So there's a lot going on in this figure. This is from Tom Seckel, my He graduated about a year ago from Queen's when I was a professor there, and is now a Gemini Fellow, carrying on this excellent spectroscopy work. The points, the orange and red points here, are HST photometry I took a number of years ago to try and look at potentially interesting Kuiper belt objects. And what is apparent from this is, one, you get just basically a straight line through the near infrared region, and there's actually a bit of a convex curvature that you see in the optical region, which is the opposite of the curvature that we see on the spectrum Checklis. And so it immediately became interesting for us because we'd never really seen anything like that in the Kuiper belt before. And so I took a spectrum from the VLT with X-Shooter, which is what you're seeing there in black. This was barely on the edge of usable, which is one of the reasons why I didn't take a look at it, and Tom decided to add it to his thesis, because he figured out how to extract spectra from this. It was just like, the signal to noise was so low that I couldn't use standard techniques to get a spectrum out. It's also the reason why the near infrared arm of X-Shooter is not shown here, is because the spectrum was just too low of a signal to noise. But Tom is amazing and wrote a very, very fancy spectral extractor, which basically saved this spectrum. And it's a damn good thing he did, because the black line is what the black wiggle is what you get out of it. And while the signal to noise is very low, the two things that you can see that are apparent are the drop off between 400 and 600 nanometers, and then a bowl-shaped sort of convex upward curvature between 600 and around 900 when the spectrum ends. That is consistent with the HST photometry, but we still wanted proof that this sort of thing was correct, and somehow Tom's extractor wasn't working, or was working. And we took a Forest 2 spectrum and you can see that in red. It's been offset for clarity, but it corroborates the general shape, at least shortward of 600 nanometers. Okay, the reason why this is interesting is actually shown in that blue curve there. So that is asteroid 38 Lida. 38 Lida is just a C-type asteroid, and that is a sense that it's basically a rock with a little bit of organic coating on the surface. And it is a very good match for the photometry and spectroscopy we have on EW95. And when I first saw that curve, I said, well, this looks like a C-type spectrum. But I mean, that can't be right. And I obviously don't know what I'm talking about, because I do studies of the outer solar system, not the inner solar system. But while Tom and I were looking at this spectrum, saying, okay, yeah, we've crossed all our I's and dotted all our T's, what's going on here? It happened to be that Alan Fitzsimmons was walking down the hall at Queen's University. And I went, hey, Alan, what do you see here? And I turned the monitor to him and he goes, why are you looking at C-type spectra? It's like, okay, we're onto something here. To give you an idea of what that looks like, here are spectra of a few different organic-rich types of asteroids, the X, C's, and B's. The C's are what you're looking for. They're the most common. X's and B's are unusual outliers that people are still trying to wrap their heads around. But C-types are basically just organic hydrated silicates. So they take a wet rock and add some CH stuff to it, and you get a C-type spectrum out. And you can see for yourself, like asteroid 106, this typical CGH one, it has the downward curvature short of 600 and that bowl shape that I was talking about. That bowl shape is indicative of iron-rich hydrated silicates, which is fantastic because this is an object in an orbit very similar to Pluto at the moment. So what the H? Well, as it turns out, it's in an orbit that is consistent with it being scattered outward and then gobbled up into the mean motion resonance that is the Plutinos. And in fact, at about the same time that we were doing this work, there was a number of studies, dynamical studies by the likes of Kuzi and Morbidelli and so on and so forth, that were demonstrating that asteroids can in fact be kicked out of the asteroidal region and emplaced in the Kuiper belt. So, aha, that's exactly what's going on here. And so this is actually evidence that there's a really big mix-up that happened in the early solar system. And it just so happens that a few of the very lucky ones survived being punted by Jupiter and ended up in the Kuiper belt itself. It also made us think about some spectra from years earlier. So this is a work from presented in 2009 by Sonia Fernassi, excuse me, of a very bright Kuiper belt object, AZ84, which is also a Plutino, it's in fact an almost identical type of orbit to EW95. And here are 3 optical spectra that they took. They have removed the continuum on this, but I mean, it's almost a relatively neutral object anyway. And you can see in at least 2 of those spectra, there is that bowl shape that we were talking about. And they, at the time, said this is possibly hydrated silicates like what Tom and I said about EW95. But unfortunately, along with this, they also published a 4th spectrum, which is not shown in here, that has bumps and wiggles all over the place. And they basically demonstrated to the community that they can't get a consistent spectrum. Or at least that's what we thought. It may very well be that AZ84 is actually another asteroid, and we just didn't get good enough spectra at the time to really believe that this was just a C-type. But I think they probably were correct, and the community didn't give them enough credit, unfortunately. I was guilty of it as well, so shame on me. But I think we're actually starting to get right into it, that we're seeing a lot of C-types in the Kuiper Belt. In fact, there may very well be a huge body of them, and we're just starting to scratch the surface of that, which would be amazing because it would really argue for a strong interaction between the outer and inner solar system at about 10 or 30 mega-years age in our overall solar system, which I think is pretty fantastic. Okay. Now on to the final poll. We're closing out here. Talk about your 2 options are the blue binaries, which bringing it back to planetesimal formation, or finding new targets for the New Horizons spacecraft, which I suspect I know which one we're going to go to. But Dennis, if you could run that 3rd poll, please.
Okay, let's get going here. Where we go? Let's see. People vote quickly. That's good. Oh, it's going back and forth.
Ha!
Hey, a few more seconds for those of you that haven't voted. It's close. Last chance. 1, 2, 3. New targets for New Horizons.
Yeah, that's what I figured. The blue
But it's
binaries is probably
by
my
one
biggest
vote.
science.
By one vote.
By 1 vote, that's great. I'll just say the blue binaries is probably my biggest science success so far and has been recently corroborated. But if you want to hear about that, go see my DPS talk in a couple of weeks. This New Horizons project is something that's been occupying my entire summer and almost all of my weekends of the summer, which I hate to say it, I've been sucked into a project again, but it's been worth it. We're running a massive campaign on Subaru right now to use the Hypersuprime cam to find targets that are visible to the LORI imager on New Horizons. So here is a rendering of the New Horizons spacecraft with all of the different science instruments that are on it. And down in the bottom left there is LORI. This is I think it's 7-centimeter telescope. It's a very tiny little thing, but it's actually been used for reconnaissance and navigation. This is what they use to steer towards Pluto and Arrokoth, but it's also a valid imager. It's got a standard CCD on the back of it, and we can take pictures of Kuiper Belt objects from the Kuiper Belt itself using this instrument, which is pretty freaking awesome. To remind you, there's the trajectory flyby of Pluto right there with the New Horizons itself. And so I'll just start this again. We are right about here at the current time, right? And so we're right on the outer edges of the Kuiper Belt right now, and the density of Kuiper Belt objects is falling off, but we can still find them. And so that's what we're doing we've had 16 nights on Subaru so far in the previous semester, and we've applied for that again to try and produce images like this. And so this is HZ84 that was found imaged by LORI and was found in the campaign to try and hunt down Arrokoth back in 2014. And so this was actually taken from within the Kuiper Belt itself. And it gives you an idea of the quality of the telescope. It is a very small thing, but the fact that we can use it for science is pretty awesome. And what we get out are plots like this one. So all these red dots are objects that were observed by the New Horizons spacecraft from within the Kuiper Belt itself. And what I'm plotting here are reflectance parameters. So if you took a blob of material that was the surface that you see and reflected light off of it, the C and B parameters describe how that light scatters forward, backwards, and sideways. And by knowing what those parameters are, we can tell a lot about the actual texture of the surface. It's called, what we get is actual phase curves, what we call them, where the angle between the observer, the sun, and the target that phase angle between 0 and more like 180 degrees, that tells you about the shadowing and the scattering properties off of the surface. And to give you an idea of what this looks like, here's what a picture of one of the plants in my garden out front that I took on Saturday when it was nice and sunny. The left side is at phase 0, or face on, with the sun behind me. And in fact, a lot of the shadow in the bottom left is actually my head. And you can see here, there's a lot of green. All the leaves are relatively uniform brightness and illumination. When you move off to 45 degrees, you can start to see a lot more shadows that show up. And then when you move off to 90 degrees, you can actually see that there's just as much dark, unilluminated leaf as there is illuminated leaf itself. And so this is a phase effect. And the macroscopic effect, like you see here, can be produced by mountains and craters and so on. There's also coherence effects that occur on the microscopic level, where you have some beams of light bouncing off of the surface and some beams penetrating before bouncing. And just like in your first year oil film experiments, you get coherence, both destructive and constructive, occurring. So some objects actually appear brighter at 0 phase than the amount of sunlight shining on them and reflecting backwards, which is pretty awesome. It's a huge project. We've got, I think, 70 terabytes of data at this point, all pumped through the LSST pipeline. The main purpose of this was to try to understand the pipeline itself so the CADC can wrap their head around it, as well, because it does something like this. The subtraction pipeline they have is amazing. And it's what we need, because as it turns out, New Horizons is still within the galactic plane. And so there's a lot of stars that need to be removed before we can even find them. And when you do it correctly, you can actually find moving objects in just the frames like this. And so that black streak with the white round dot right beside the E there on the end of the sentence, or the end of the title, that is a known moving object. The black streak is due to the fact that we produce a template from all of the frames we take in a night, and then subtract that template off, and it produces a negative well around the object. Unfortunately, this is just a cost of doing business when using image subtraction, but it gets rid of all the vermin for me, which is all the stars and galaxies in the sky. Then we reached out to our citizens to help vet shifting and stacking. So what we do is we take all of those subtracted frames, and then we shift them at rates and angles of motion that would counteract the known rates and angles of motion of Kuiper belt objects, or at least objects at the distances we care about, or on the orbits we care about, to try and find. And what I'm showing here on the right are stacks that show that. So we divide the sequence into 3 separate stacks for a sanity check. And the angles are shown in the 3 columns, and the different stacks are shown in the rows. And what you're seeing here is cycling through different rates of motion. And when you get the rate of motion correct, all of the light of the source that is moving in the frame gets blopped onto itself, and you get a nice round detection, is what you can see here. So this is actually one of the targets we will be observing with New Horizons in December, which is pretty freaking awesome. We found it a few months ago, and we're already turning the spacecraft towards this body. This has been a huge effort, because there's been, sorry?
Wes, could we think about wrapping it up? Or?
Yep, this is literally the last slide. So
Perfect.
Thank you.
Thank you.
There's been a huge number of people helping. We've basically, I shouldn't say citizen, because these are relatively trained astronomers, people that understand what images look like, but there's about 40 of us that have been going through thousands of vetted sources to try to find the 74 new Kuiper belt objects we have. 13 of them will be observed by New Horizons over the coming probably couple of years, with 8 of them being observed in December. And so if we go back to this plot where we have 6, we're going to be adding about 35 total from the program to really try and understand the surfaces of these things. And my expectation is that, much like the compositions showing up as different classes of Kuiper belt object, we will actually see those classes show up in differences of their surface as well. And so it's my hope that when we have a sample of 35 plus objects, we can start to disentangle the physical processes that occurred during formation before these things got scattered out into the Kuiper belt. So it's a really fun project, if not completely consuming. And so with that, I'll leave it to the end here. There's that figure from Col-OSSOS that I've shown, and here are the 4 questions that I hope are in your minds, or at least partially in your minds from seeing this talk. Obviously, we've got quite a long ways to go before using compositions as tracers of formation are sorted out. And with that, I will happily take questions.
Amplify that by a few. Thanks, Wes. Excellent talk. Audience, thank you for choosing interesting rabbit holes to go down. Although I suspect any of the rabbit
I
holes,
hope that was fun.
I'm sure any of the rabbit holes would have been great. A question from earlier, but it may not be any relevant at the moment. But is the redness a measure of the age of the surface? And I suspect
If you went down the right rabbit hole, I would tell you yes. In a way, there is. There's two things that matter towards the redness. It's how much irradiation has occurred on the organic that is in question, and then the organic in question. And so, if you start with, say, a pure methane surface, you can make it go red with solar irradiation. But if you start with, say, methanol, even just that inclusion of one oxygen atom changes the reddening rate and the overall shape of the spectrum afterwards. So those two things are tangled together in a complex fashion that we don't quite yet understand.
I think this refers to the one object you showed you found in the Subaru data. How faint is that target?
That was 24th magnitude, which our detection limit is just past 26 at the moment. They have to be about 21st magnitude as visible by New Horizons, but of course New Horizons is only a couple AU away from these things, so they're a heck of a lot brighter out there. But this is, of course, the power of Subaru. 24th magnitude is actually very bright for our detection sample.
Another question in the chat window. Is it no longer called the Edgeworth Kuiper Belt?
Uh, Edgeworth and Kuiper and other names really depend on the bias of the speaker. I call it Kuiper because that's the one that I learned first. There is some argument as to who predicted it first, and so some people like to call it the Trans-Neptunian region to avoid that terminology entirely. I've just got bad habits.
If any other questions, please raise your hand in the participant window or type it into the chat window. I'll have a question in the meantime. So this astronomer assisted searching for new objects, is that something that sort of an AI-based analysis technique could be applied to?
We actually have a student working with JJ Aram. She is basically doing exactly that. She's trying to take the huge swaths of Subaru data and generate an AI that can avoid the human vetting, because it's the most expensive part, well, one of the most expensive parts of the whole project, and quite frankly is very prone to error when you're looking at 25,000 sources. You have a tendency to go blind before the day is over.
Yeah, absolutely, absolutely. Okay, Sam, you have a question. Go ahead.
Hi, Wes.
Hey, Sam.
So is there anything in I'm gonna say it wrong, at Echolocus? Is there anything weird about its orbit within the Plutinos that tells you that it's been captured, like very high libration amplitude?
Good
or
question.
something?
So a checklist is the Centaur, sorry. You're meaning EW95.
Yeah.
EW95, AZ84, and one other candidate C-type that we have from the Colossus project are all at about 25 to 27 degrees inclination. They're all very hot, dynamically speaking. And that's like right on the upper edge of the inclination distribution for the Plutinos. So that is consistent with the idea of a very strong, as you know, very consistent with very strong scattering and capture afterwards.
Yeah. Are they cosine or?
EW95 isn't. I think AZ84 is, but don't quote me on that. I haven't looked at that in a long time.
Okay, cool.
Anybody else want to raise their hand or type a question? I'll have another one. Talking about, the less red KBOs being C-type asteroids, you indicated it's evidence for interaction between the inner and outer solar system. This seems it must have been a one-way interaction and that we don't find any KBOs in the asteroid belt. Is that right?
It isn't actually a one-way street. It's a two-way street. In fact, Hal Levison was argued first that there may very well be a Kuiper belt object or two in the asteroid belt before we realized that there are asteroids in the Kuiper belt. It just so happens that for Kuiper Belt objects, Jupiter is a big jerk in the sense that it prefers to skip things out of the solar system rather than emplace them in the terrestrial region, which for us is actually a really good thing, because if Jupiter weren't doing that, we'd see a lot more big impacts on the Earth. So there is a route forward in bringing objects out to in. It's just a lot less common, so we think.
Okay. Any other questions? Doesn't seem to be. So thank you, Wes. That was a fascinating talk. Excellent. And
Thanks.
I love the format. I think
Thanks everyone for joining. I appreciate the
nice
audience.
to see other people take that up.
Stay healthy.
Okay. Yeah. Stay healthy, everyone. Have a good week. Bye.
Thank you.